Hello chemists, and welcome to video 6.1.1, our first in a series of videos on thermodynamics. So this is our 6.1 lesson. The first thing we are going to start our discussion talking about is internal energy. And that has the symbol E-int, int for internal. And this triangle, of course, is delta, means change in. Before we begin talking about calculations and how to do problems involving thermodynamics, first we have to define our system and our surroundings. So our system is the thing that we're usually looking at. So usually in our case, that's a chemical reaction, usually a chemical process, something inside a container usually, and the surroundings, which is the rest of the universe all around it. So system, right in the center, we can imagine maybe a chemical reaction happening here, and the surroundings is everything besides the system, including the entire universe. So there are a couple kinds of systems we have to be concerned about. Isolated systems are almost impossible really to have, but we're going to talk mainly about open and closed systems. Now, what's the difference between these? The difference really comes into play when we're talking about the movement of matter and energy between the system and the surroundings. In an open system, matter can be exchanged into and out of the system as well as energy. So you can think about something like an open beaker for this. In a closed system, matter can't be exchanged, so the matter is maybe stuck inside. So you can think of a beaker maybe with a lid on it, for example. And energy, though, can move in and out, right? So that can go in and out of the system even though the matter is stuck inside. In an isolated system, which we don't normally really see, nothing would be able to move. No heat, no energy would be, and no matter would move in and out of the system. So the internal energy of a system, again, that's the symbol is E-int, is the sum of all the kinetic energy which contributes to the temperature. So again, our temperature is our kinetic energy. And it also includes our potential energy. And that potential energy comes from the attractions that are between particles. The first law of thermodynamics states that an isolated system, one in which no matter or energy can be exchanged, the internal energy of that system is conserved. So the change in internal energy would be nothing. So it's conserved, that means there's no change at all. Energy can be converted from one form to another, like kinetic to potential energy or to chemical energy, but the total energy cannot increase or decrease. However, like we said before, no system is truly isolated, so the internal energy of a closed system can change in two ways. So either by heat flow, either heat flowing in and out, or the system doing work. And we can represent that with this equation. Delta E-int, so the change in the internal energy, equals Q plus W. Q stands for heat, W is work, so it's the summation of heat and work together. So what are heat and work? So heat has the lowercase letter Q, and that's the flow of thermal energy between the systems and the surroundings, from the object of higher temperature to that of lower temperature. Heat never flows the other direction, right? So if you put the classic example is putting a cold spoon in a bowl of soup, that heat travels from the soup into the spoon. So you always go from high to low temperature. And work has the symbol W, and so it's a lowercase w, and that can be measured by the energy from the expansion or the compression of a gas. And we are going to use this equation for that. W, or work, equals negative pressure, so P for pressure, times the change in volume there. We also have an equation for heat, to calculate heat. So Q equals mc delta T. So where Q is the heat, M is your mass, C is defined as your specific heat capacity, and that's going to be different for every substance. That is a constant. And delta T, the change in temperature, which is final temperature minus your initial temperature. So putting this all together and looking at this in the terms of a system that we can understand, we're going to look at this piston. So for this process with this piston, like an engine, you're going to put heat in. And when heat goes into a system, that is an endothermic process because the system is going to absorb heat. Q is going to be greater than 0, so heat's going to go in. Work is going to be put in the form of compression, right? So we're going to compress that gas in that system. W is going to be greater than 0, compression. And then here is our system. We have our same equation we had before. So the internal energy, the change in internal energy, is the sum of the heat plus the work. And then the heat that comes out that's going to be less than 0. Q is going to be less than 0, so we're going to have our negative sign over there. So negative exothermic, positive endothermic over here. Our work is going to be coming out in the expansion phase, and W is going to be less than 0. So let's see what all of this means through an example. Example 1, we have 20 gram sample of argon in a cylinder with a piston at 30 degrees Celsius. Heat flows into the cylinder and increases its temperature to 40 degrees Celsius. The cylinder expands against a constant pressure of 95.5 kilopascals from 21.5 liters to 23.5 liters. By how much has the internal energy of the system changed? Argon has a specific heat, so it gives it to us there, and the conversion for the units for joules. So 1 joule is equal to 1 liter times kilopascals. We're going to want to pay attention to those later when we're doing our calculations. So really this is asking us to find the internal energy and how much that internal energy has changed. The symbol for that mathematically is going to be delta E int, right? So that's what we're going to try to find. We know from above our equation for finding that is the sum of the heat plus the work, but we're not given the heat plus the work, so we're going to need to find the heat and we're going to need to find the work. So this is a good time to pause the video and try to tackle this problem, keeping in mind you need to find heat and find work, and you're given your equations above and your units that you will need to solve that. So please pause the video and then come back to check your answers. All right, welcome back. So hopefully you were able to pause and tackle this problem. Let's review now. So I'm going to find my heat first. So I'm going to use my equation for heat. Q equals mc delta T right here. Mass times the specific heat times the change in temperature is going to give me my heat. So Q equals mc delta T. And I'm given all the variables I'm going to need in my equation. So I'm just going to go ahead and start plugging those in. My mass of my argon, so a 20 gram sample of argon, is 20 grams, 20.0 grams. The specific heat of argon is given to me here, 0.52 joules over grams times degrees Celsius. So again, I'm going to keep all my units here so I can make sure this all works out. 0.52 joules times inverse grams times degrees Celsius. Inverse, that's the same as writing that on the bottom of the fraction. We remember from previous lectures. And the change in temperature. So final minus initial. So the final temperature is 40 degrees Celsius and it started at 30 degrees Celsius. So I'm going to write 40 degrees Celsius minus 30 degrees Celsius. Of course, you could have just written 10 degrees Celsius here, and that would be totally fine as well. When I plug this into my calculator, I got a positive 104 joules. Just go back and make sure that your units work out. So let's go ahead and cancel these units out. Our inverse Celsius cancels our Celsius here. These are subtracted, so you can treat that as 1. Your grams cancel your inverse grams, and you're left in just joules, which is what we want for heat. That's our unit of heat. All right, so we found the heat. Now we need to find the work. So we'll use our equation that we had above. Work equals negative P times delta V. So work equals negative pressure times delta V. So I'm given my pressure. I believe it is 95.5 kilopascals. So I'm going to go ahead and plug that in. Don't forget your negative sign here. We're going to carry this negative sign over. So negative, and then in parentheses, my pressure, 95.5 kilopascals times my delta V, which is my change in volume, final volume minus initial volume. My final volume is going to be 23.5 liters. My initial volume started out at 21.5 liters. And again, you could have just subtracted these and written the 2 in there. That would have been fine as well. Now, here, we're going to need to plug in the units for joules, because for our work, we're going to want to get our answers in joules, and we want to be able to convert to that. So I'm just going to use my conversion factor for joules right here just to get my answers to come out in joules. So 1 joule is equal to 1 kilopascal times liters. I just wrote that under the fraction. It doesn't matter. You can write it however you like. So canceling my units here, kilopascals cancel. These kPAs are on the bottom of the fraction bar. Those cancel. My liters cancel out there. And I should be left in joules. Yes, I am. Perfect. So when I plug this into my calculator, I get a negative value, so 191 joules. Now, what do these values mean? Before we move on, let's kind of discuss that a little bit. So the value that I got in my work equation right here, this is negative. This is work out, right? And so we can tell if the work has gone out of the system because the W is less than 0. So that's our work out. Here, this is heat in. This is an endothermic process here. We can tell because we have a positive sign there. And we can tell also that Q is going to be greater than 0. Anytime we have Q greater than 0, positive sign, that's going to be heat in, endothermic. All right, so we found our requisite heat and our work. So the only thing we have left to do now is put that together in our overall equation and figure out the change in internal energy. So the change in the internal energy equals heat plus work. Plugging in the heat and the work I got above, I got positive 104 joules plus a negative 191 joules. Mind your signs, be careful with that. Overall, that's going to give us negative 87 joules. Negative 87 joules. So therefore, we can tell that the system loses 87 joules of heat, or of energy rather, to the surroundings. So therefore, the system loses 87 joules of energy to the surroundings. Okay, and again, just a quick recap, we can tell that it's losing energy to the surroundings because it's a negative sign, so it's going to be exothermic. If it was positive, it would be gaining energy, that would be endothermic. Okay, that is it for video 6.1.1. I'll see you in just a little bit for video 6.1.2.